these are the basic formulas in quantum mechanics. This really is the defining relation in quantum mechanics, and it distinguishes quantum mechanics from classical mechanics altogether. Hi, welcome back once again. So for those of you who are joining me for the first time in this channel, in this course, we study this book by David Griffiths on quantum mechanics, and I try and keep it at the level of undergraduates and high school students. So most of the calculations that we do in this course are very explicit. And of course, since you guys are here, you probably know that this is the name of my channel, and this is my Gmail ID, where I take questions. Like if you guys have some clarification, if you have some confusions that you want clarified or something, I generally take emails on this mail ID, and you feel free to reach out to me. And so so let's begin. It's lecture 4. In the first lecture, we have actually studied or introduced the Schrodinger equation itself. This was lecture 1, and in lecture 2 and 3 we worked a bit about, very minimally, we worked about probability theory. This is lecture 2 and 3, and the links for these videos would be in the description box. At any rate, I've also created a playlist, so you guys can go and check them out chronologically there. So in lecture 4, we tie these things up together. Okay, that is sort of the idea. So let's begin. So I guess a question, I guess a question that you guys should have had till now, from those of you who are coming directly from after studying classical mechanics, is okay, all this is very fine. This is some really fancy stuff, things happening with probability theory with some fancy equation called the Schrodinger equation. But eventually I need to know what is the position. And for example, at the very basic, I want to know what the position and momentum are of the particle is. Like, what is the analog of position and momentum, or how do I calculate the position and momentum of a particle in this fancy quantum mechanics that we are trying to develop here, right? For example, in classical mechanics, we already know the answer to this question, right? For example, if someone gives me a force, from Newton's law, this is m d2x dt square. So if someone gives me the left hand side, I know I can integrate and I can find out the right hand side. And for example, I would know as a function of t, of course, as I had mentioned in lecture 1, that this x would be determined by, it will have two undetermined coefficients. X of t would have some undetermined coefficients, say c1 and c2, and it would be a function of time. Why two undetermined coefficients? Well, because there's a 2 here. So these are the constants of integration for you. Once you fix it from using boundary conditions, you would probably find say a trajectory for this particle. This is, say, x of t and a t. Say you would have a trajectory like this in classical mechanics, right? And the momentum would be given in classical mechanics, again, would be given by m times dx dt. So mv, right? So if I know x as a function of t, if this is known in principle, then this is known, right? I can just take the derivative. So this is classical mechanics. So the question is, what is the analogous business in quantum mechanics? That I want to ask. What happens in QM, quantum mechanics, to these x and p, is the question that I want to address in this lecture. Well, this is where we started using probability, and we, in the last two lectures, we developed this idea. This expectation value of x would be given by an integral over all x. Rho of x, right? Right. Which we later took to, which we in quantum mechanics, this was simply tx x mod psi x of t, and this wave function was a solution of your Schrodinger equation. So that's how this is a solution of Schrodinger equation. So that's where Schrodinger equation fit in this formalism, right? Good. So in quantum mechanics, then the exact analog of classical mechanics would hold. So your momentum operator, or the expectation value of the momentum operator rather, would be given by mv, right? This is the formula that we just used here. Except that these are now expectation values of some operators, right? So we always have these angle brackets. We will understand a bit later what these angle brackets mean. You should be uncomfortable, or you should not be very clear right now as to what these angular brackets are. It will be clearer later, later in the course. These are expectation values of some operators, okay? But for the time being, these are just some words, so don't worry too much about it. But yeah, but just focus on like what the physics is trying to tell you. So this would be this expectation value of your momentum operator is just m times v. This is the same, we literally borrowed it from classical mechanics, and v is m times v is ddt of expectation value of x, right? Again, literally ripped off from it's like the same formula from classical mechanics. So exercise, let's evaluate, say, expectation value of v, okay, is how much in quantum mechanics. Well, I literally told you the definition of expectation value of v. It's this, and I know, for example, what this guy is. So it's dd, sorry, I shouldn't use the red color unnecessarily. ddt of x all space for the time being, I'll just denote it from minus infinity to plus infinity. Tx x mod psi x of t whole square. Again, if you go back, this was the definition of expectation value of x, right? So nothing happened here. Note that this ddt has nothing to do with this dx has nothing to do with ddt. So I can pull this inside and write this as dx. Note x has nothing to do with t, so I can write this as del psi pa del psi t times psi plus psi pa del psi x of t. Because this, I think I need not explain, because this is by definition psi star psi. Right. And the ddt operator distributes, so that's what I wrote simply. Now this is where, for example, Schrodinger equation comes in. Why do I need Schrodinger equation here? Because I know, for example, it's equal to minus h squared by 2m del square psi x of t del x squared plus vx psi x of t. Note here, this is a real function. This is real. This is just the Planck's constant divided by mass. Square of the Planck's constant divided by mass. So if I take a complex conjugation of this expression, what am I trying to do? Let me tell you where I'm headed. I just want to figure out this guy, right? Using Schrodinger equation, simply. So this would give me... Okay, maybe I'll let you do one step. So check. This is just one line, homework. Okay. Let me be even kinder. Let me do one step for you. So let me take the complex conjugation of this equation. CC being complex conjugation. So this I picks up a sign. We have a little psi star. As I said, this is h squared by 2m is real, so it doesn't change sign. Neither does this term change sign. Also note, as I mentioned, this is real, so there is no reason for me to put a star here, right? Only the wave function is complex, so that's the only guy that picks up a star. Okay, good. So this is equation 1. I have literally done everything for you. Equation 2, from 1 and 2. Step 1, say step 1 multiply equation 1 by psi star from left, and step 2 multiply equation 2 by psi from right, and this is a tiny one line check that you should do just to ensure that you're following. You should get this expression psi star plus del psi star del psi t psi is equal to 1 by IH cross h cross square by 2m times let me pull out a minus. Actually, you should get minus h square by 2m times psi star del 2 psi x square del psi x square minus del 2 psi star del x square times psi. This bracket is this bracket is here, is this bracket. Okay, this is a one line check just from literally I've told you the algorithm, like how to get this. The point being that this guy cancels, that's all. This guy cancels. Okay, so this is an intermediate step. The next step would be, this gives you is equal to I h cross pi 2m tilde x psi star till psi till x minus till psi star till psi star till x psi. This is what you should get. A total derivative, okay? Total derivatives are always nice, right? Because you can really integrate them quite easily. So please kindly derive all this. This again, this is just one line, one step, just to, you know, just to ensure that you are sort of following the math. So now I go back and I write this. This was the left hand side that we had started from here. This is the left hand side that we have started from here. We write this to be is equal to I h cross pi 2m TDX x times TDX psi star del psi del x minus del psi star del x psi. Maybe I want a bracket here, right? This is what you get. Well, why is that? Because we have already figured out the intermediate step. This guy is a total derivative. This is this guy, right? This is what I had written here. And this guy was simply the expression for this. So that times x, that times x integrated over ddx is your velocity, expectation value of velocity. So now you know what to do. This is almost literally begging you to integrate it by parts, right? So this is minus plus, sorry, IH cut 2m how do I want to write this? Say x psi star del psi del x minus x del psi star del x psi. This is evaluated at the boundary. So what have I done? Let me explain. I've just pulled out. I've just integrated this. I've pulled this out here, and then integrate over x. So you get a boundary term. This is the boundary term, right? This is the boundary term. But in trying to pull it out, I'm left with another piece, right? So it would be this guy minus IH to m. Now your ddx needs to just act on this, right? Which is literally 1. So yeah. Del psi del x psi star del x psi. Do you agree with it? Let me again be clearer, like literally be pedantic. So what I've done is pulled this ddx out here and integrate it. So that gives you this boundary term. And since I had pulled it out, I now need to subtract the remaining term, which is this ddx acting on just x. Well, ddx acting on just x is 1. So you're left with just this guy, which is this guy, integrated over x, right? Do you agree, right? Okay, now this is something that you will do all your life in physics. You will claim that this boundary term vanishes. This boundary term vanishes. Why? This is important because your psi and psi star need to go to zero, right? At x going to plus minus infinity. Why? Why does it need to happen? Because you need to demand, recall that in the first lecture, we had said that this guy needs to be 1, properly normalized, like there's a normalization factor for this size, but that's just a constant function. This needs to be 1, which implies, this implies that necessarily your psi xt needs to go to 0 as x tends to plus minus infinity, which is the boundary in this case. So this is a crucial point here that we have arrived, that your wave functions need to go to 0 at the boundary for your probability to be for their probability interpretation to make sense, right? This is a result that we get immediately as a consequence. Good. Now we are nearer. So as per the discussion, this term vanishes because this guy vanishes and this guy vanishes, right? So you're left with expectation value of v is simply minus IH. Let me just copy it. Let me be lazy and copy it. Copy. Paste. Am I being too slow? Like, let me know, you guys. Like, if you guys are literally following, you can drop a comment and say this is like too easy or I'm being too slow. Should I be a bit faster? Like, I try and like literally explain every step. Often, that's not necessary. But yeah, let me know if you guys feel this is too slow. Okay, so this I claim, again, you can use basically partial integration techniques, and this I claim is simply minus IH cross by 2m. I beg your pardon, not 2m, m. Tx size that's it. Okay, what have I done? To give you a hint, I have just used partial differential sorry, what am I saying? I have just used integration by parts here. Okay, so you pull out the ddx, so the full term needs to again disappear because your wave functions vanish at the boundary, and your ddx acts on the other guy with a sign which is equal to this guy, but so that sort of cancels the 2 here. Okay, good. Now we are done almost. So your p is m expectation value of v, and I already get a very nice formula for this, right? So this is an important result here, and this is one of the central results in quantum mechanics essentially, and it tells you, what does it tell you? Well, it tells you two things. First, if someone gives you the wave function, it tells you how to find the momentum of that particle. This is the expectation value of the momentum, or loosely speaking, the momentum of the particle. And it tells you that if someone gives you the solution of the Schrodinger equation, this integral gives you the average value of the expectation value of the momentum of the particle. But more importantly, it tells you in quantum mechanics, momentum is given by this minus IH cross tilde x, just as position is really given by x. Oh, just to be very clear, this is a momentum operator. Sitting here. This is the position operator. So in quantum mechanics, momentum is given by, loosely speaking, momentum is given by I delta x, and position is given by x. How do I know the latter? How do I know that position is given by x? Literally, that's what we have been doing, right? The expectation, look here. So the expectation value of x has just been given by x, for example, times the wave function. So the operator x is instructing you to multiply the wave function, mod square of the wave function, by x. So x in quantum mechanics, the position operator, is a multiplicative operator. It simply instructs you to multiply whatever sits on the right hand side. Likewise, for example, the momentum operator instructs you, it acts as a derivative operator here, and it instructs you to, it acts as a derivative on whatever sits on the right hand side here. Okay, so these are the basic formulas in quantum mechanics. These are the basic formulas in quantum mechanics. And I want to do one last thing. This will be quite instructive. So now I know, for example, how operator x acts. I know this, for example. In this representation, it acts multiplicatively. I know how p acts. In this representation, it acts as a derivative. As an aside, by the way, before I proceed, let me say something. As an aside, this is probably not there in the Griffiths at this stage. This is the representation in the position basis, so-called position basis. There would be an equivalent momentum basis. This is an aside, so if you don't understand this, it's okay. I mean, you'll survive. You don't need to understand this, but this is just a general information, and for those who have studied quantum mechanics before, they will understand this a bit more, I suppose. There, your x acts as IH cross del, your x axis, del p, and p axis, literally p, in the momentum basis. Note there is a crucial sign difference here. So later, if you guys take up quantum field theory, you'll probably use this basis a lot more, the analogous basis for quantum field theory, and they are related actually by Fourier transform, because we know, for example, that x and p are conjugates. But this was an aside. If you don't follow, that's great. That's absolutely fine. There's no problem. Okay, let's get back to where we were and say I know how x acts, the operator x acts in momentum in position basis, how the operator p acts in position basis, and maybe I just want to, for some reason, for some crazy reason, I want to figure out this guy, the commutator of the position and the momentum operator. How do I question how do I figure it out? This is actually telling you, what this question means is that it tells you to act it on the test function. This is called the test function in physics. Test function. Fn is function. Henceforth, in this lecture, it would always be function, for example. Okay, good. So let's see what this object is. Let's calculate this. It's easy to calculate. I know x acts as x. This acts as minus del del x in this basis times f. This is a commutator. I hope you know what a commutator is, by the way. Yeah, a commutator of two objects is simply, this is definition, AB minus BA. Surely you know this, right? Okay, I'm not sure. Yeah, but anyway, this is definition. So minus acting on x of f. Does it? Do you see that it follows from here, right? So A, B acting on f minus B acting on AF, right? Because I'm evaluating this guy. So there is an F here and there is an F here. This is very easy. This gives you, say I want to pull out minus IH cross. So this gives you del F del X minus del X, which is 1, F minus X del F del X. This cancels. So is equal to IH cross times in, right? Times, sorry, I'm being too fast. Times F. Because this is, of course, this is 1. So immediately you get this relation in this basis, x comma p, commutator of x p is h cross f. And this is the fundamental relation in quantum mechanics. The commutator of the position operator and the momentum operator is non-zero. This is the fundamental relation. In some books, for example, if you, I think, follow R. Shankar, this is the starting point in quantum mechanics. That the position operator and the momentum operator, they don't commute. It's non-zero on the right hand side. They commute if you go into the so-called classical limit. What is the classical limit here? Well, the classical limit is h bar tends to 0. So you say in that limit, you have these guys. In that limit, you have x. In that limit, okay, it's important. Going to 0 as h tends, if your h goes to 0, and then you recover your usual classical mechanics. And by that I mean there are no non-commuting operators in classical mechanics, right? There is nothing that doesn't commute in classical mechanics. Why is that? Well, because in classical mechanics these are all functions, as opposed to quantum mechanics, these are all where they are operators. So functions always commute. So f1, f2 for arbitrary functions would always be f2, f1. So in classical mechanics, everything commutes. It commutes. So to highlight once again, this really is the distinction between this really is the defining relation in quantum mechanics, and it distinguishes quantum mechanics from classical mechanics altogether, where you reproduce the classical results in the limit h bar goes to 0, which is sort of what I did here. And you reproduce the known facts that in classical mechanics everything commutes, right? So yeah. So great. This is where I wanna say stop today, and yeah, see you in next class.